This is section 13.2, part D. We're now going to be looking at using double integrals to do some geometry, starting with finding the area of a region. It's probably a somewhat familiar problem because we've looked at it in Calc 1 and Calc 2. But if I've got some region, say bounded by a couple of graphs, and my ultimate goal is to find the area of the region between those two graphs. And let's see, let's call this one y equals f of x, and that one called y equals g of x. You definitely learned techniques for finding that area back in Calc 1 and Calc 2. However, I'd now like to talk about how we can do the same problem using a double integral. Essentially, what this is going to involve is imagining how that area relates to a particular volume that we can visualize. If I were to redraw this in a three-dimensional coordinate system, so my x and y axes over here are now x and y axes over there, then this same picture, let's see, what would that look like? It's all on the positive side of the y, and it looks to me like I've got something that kind of looks like this, more or less. So there's that same area shown in the xy plane of a three-dimensional coordinate system. If you imagine creating a three-dimensional object is how I'm going to describe it, that's exactly 1 unit thick, directly on top of that region. So I'm going to imagine that I'm going to go up exactly 1 unit. And create that same basic shape up here. I've now got a three-dimensional object whose bases are the region R. The volume of that three-dimensional object is just the area of the base, the area of R, multiplied by the height, which is 1. Oops. So in fact, the volume is really equal to the area of R numerically. I know that sounds kind of funny to say because volume and area are two different things. They have different kinds of units, right? But numerically, because the height was 1, the volume is actually equal to the area, just with different units. Therefore, what we're going to be able to say is if I think of this top surface at a constant height of 1 as being the plane z equals 1, I could now find my volume, which is the same as my area, by taking the double integral of my height function, which is just z equals 1, dA. Oops, I'm sorry, you couldn't quite see that. So again, volume is going to be the same as area numerically. I'm taking the double integral of the height function, which is 1, dA over the region R. So what we're basically saying here is to find the area of the region, essentially imagine you're finding the volume, but with a height of 1. All right, let's use that technique to do example 9. I'd like to find the area, using a double integral, of the region bounded by y equals x cubed and y equals minus x squared plus 2x. Those aren't terribly difficult equations to graph, but as long as we've got technology, let's go ahead and take a look here. I've actually graphed them on Desmos right there for us, and you can graph them. Oops, sorry, I think I lost that. Let me find that again. There we go. I've actually graphed them on Desmos. You can graph them on your calculator as well, of course. And what you can see here is our x cubed curve here in red, and then our minus x squared plus 2x curve in blue. And while I'm right here, I'm just going to take a look. Notice that intersection point is at 1, 1. It intersects here, of course, at the origin, 0, 0. And then over here at negative 2, negative 8. So I'm just going to go ahead and copy that diagram so I can draw on it in my problem. So here we go. We had our upside down parabola. Y is equal to negative x squared plus 2x. And then we had our cubic function. Y equals x cubed. Kind of like that. And there was an area here and another area there. This intersection point was at 1, 1. And then this one down here was, I believe, at negative 2, negative 8. And again, you can verify all that with a calculator graph or a Desmos graph. All right, so to use a double integral to find my area, I'm going to have to do this in two pieces. I've got a section down here in quadrant 3 and a section up here in quadrant 1. I'm going to do the quadrant 1 section first. I'll call that A. And if I imagine drawing little vertical rectangles here, then my area is the double integral. By default, when I want area, I use 1 as the height function. And then since we're going to go with vertical rectangles, we'll go in the order dy dx. For the y values, the bottom of the rectangle is on the x cubed curve, and the top is on the parabola, giving me my limits of integration for y. And in the first quadrant, the x's would go from 0 to 1. This isn't too bad to integrate, since I'm just integrating the constant 1 dy. I will simply get 1y as y goes from y equals x cubed to y equals minus x squared plus 2x. And let's see, plugging in the top limit, I'll have minus x squared plus 2x. Subtract plugging in the bottom limit, x cubed. And at that point, it's simply a calculator problem. When I plugged that in, I got 5/12. Now, what I'd like to point out to you is that this is completely consistent with what you learned in Calc 1 and Calc 2. Notice that if I hadn't done the double integral, but instead had started right here, this is just the top minus the bottom. Top curve, the parabola, minus the bottom curve, the x cubed curve, and integrating between the intersection points, which is how you learned to do these problems before. We're just simply looking at an alternative method, and one that's going to set us up well to learn some more stuff about multiple integration later on. All right, let's also do the part over here in quadrant 3. I'm going to call that B. And the area here. Once again, I want to do it as a double integral. To do area as a double integral, we always use 1 as our height function. I'm once again going to think of vertical rectangles here. So I'll go in the order dy dx. And the only real difference is this time, integrating bottom to top for the y's, the bottom function here is actually the x cubed function. Excuse me, I said that wrong. The bottom function is actually the parabola. I probably should have color-coded those a little bit. This is my parabola right here. So the bottom function is actually on the parabola, and that would be the minus x squared plus 2x. And the top of my rectangle is on the x cubed curve. The x values in quadrant 3 go from the -2 to the 0. So, integrating that, once again, I'm just integrating the function 1 dy, which is going to give me y, from y equals -x squared plus 2x to y equals x cubed. Plugging in the top one, I've got x cubed. Subtract, and make sure you do subtract the whole quantity, a -x squared plus 2x. And as long as you include the parentheses, you can type it in just like that, or you can distribute the minus sign first before you type it into your calculator, your choice. When I did that, I ended up with 8/3. So my final answer here for the total area between the two curves is just going to be the sum of the pieces. 5/12 plus 8/3, which is going to give me 37/12. So again, area using a double integral, always integrate 1 as your integrand, and then just set up your limits of integration using the rectangles like we've been doing. All right, the next thing I want to take a look at is using double integrals to find volumes. This is actually where we started talking about double integrals in the first place, so we're sort of going back to it now. And I want to talk first about using a double integral to find the volume of a solid above or below a region in the xy plane. If we imagine here, and this is sort of a repeat of a diagram we've already seen, that we have some surface up here. I'm going to kind of draw a generic surface. So let's just say that's the surface z is equal to f of x and y. Our goal right now is to say, if I've got a particular region down here in the xy plane, and again, I'm going to kind of make a little generic one. This is the R. I use that to sort of cut out a region above it on this surface, and that region becomes the top of my solid. And our goal was to find the volume of this whole solid in between here. Again, we've looked at this before, so I'm just going to remind you of what we already know here. To find that volume, we simply take the double integral of the height function. Our height function being the z value, f of x and y. We integrate over the region R, dA, where dA is either dx dy or dy dx, depending on what's more convenient for us to work with. To find a volume, we always integrate the height function. We'll come back to that in just a little bit. All right, in example 10, we would like to find the volume of the solid, and I'm going to specify just in the first octant, bounded by the xy plane, and the surfaces z equals 4 minus y squared, x equals 0, and y equals x. Now, one of the things that you're going to probably face challenges with here is trying to visualize what's going on. Some problems you can do almost without visualizing, but others the visualization is going to be extremely important. So I'd like to give you a few different ways of thinking about this. I will, generally speaking, try and sketch pictures by hand wherever I can. It's just good practice for us to do the visualization. But I'd also like to give you a couple of tools. Since you're now working at home, you may or may not have access to Maple. Maple did offer a relatively inexpensive $30 option for you to use to finish out the course, and if you're willing and able to purchase that short-term access to Maple, certainly by all means I encourage you to do that. There's also a three-dimensional graphing program called Geogebra that we can use. It's not nearly the sophistication of Maple, but it will at least help us to visualize graphs. So we're going to sketch this one by hand, and then I'm also going to show you what it looks like using both of those softwares, so you can kind of see the different tools that may be available to you. All right, I'm going to start by hand. Looking at this function, I see this has got a missing variable, right? There's no x in that equation, and that means that this is a cylinder parallel to the x-axis. So, if I do a little three-dimensional sketch here, I know that z equals 4 minus y squared just in the yz plane is an upside-down parabola. It goes up to a height of 4 and then comes down, and it would hit the y-axis here at plus and minus 2, since that would be the zeros of that function. Oops, that would be a positive 2, that would be a negative 2. I'm not going to bother showing anything below the xy plane, since the xy plane is one of my boundaries. Okay. The cylinder then would come out parallel to my x-axis, like so. All right, x equals 0. That's the yz plane. And I've actually already kind of accounted for that. I didn't go beyond, I didn't extend backwards behind the yz plane, so I'm good there. Finally, I've got y equals x. That's another plane. Since z is not mentioned, it's a plane parallel to the z-axis. I do know that y equals x is just a diagonal line in the xy plane, like so. And then if I just imagine that plane vertical, including the x-axis, it's going to slice through my cylinder, kind of like so. So here's that flat-sided plane. Y equals x. Here's the curved surface of the cylinder. Z equals 4 minus y squared. And then the base is going to be in the xy plane itself, since it's bounded by the xy plane. You can kind of see down there, what we've got is a triangle. This triangle down here is the base, and this is my region R in the xy plane. R is going to be really important because R is what determines my limits of integration. So I often then take a moment and redraw R all by itself, just in the xy plane. So as I'm looking at the R here, notice that this line right here is y equals 2. And this dotted line that I had drawn, remember that was the plane y equals x, so that's the line y equals x. And then the y-axis itself is another boundary over here. And so R ends up looking like this when I draw it in just the xy plane. So this is just a picture of R. Okay. As we set these problems up, I'll always try to draw R on its own because, again, R is what I use to find my limits of integration. So R is especially important. Before we actually set up our integral this time to find the volume that we want, I'd like to go ahead and just take you through a little journey where we can kind of take a look at how we could also see some of these things using technology, because that's going to be important for you when we get complicated things that are hard to visualize by hand. So I think we kind of know what this looks like. If I go to Maple, which again you may or may not have access to at home. If you do, great. If not, I understand. Oh, excuse me. Well, here, Maple. There we go. Going back and forth here, I apologize. There we go. All right. Here is Maple. I did the with plots to get everything I needed up there. And you'll notice that I did an implicit plot 3D. I've graphed z equals 4 minus y squared. I've graphed y equals x and x equals 0, all three functions. And I set up some windows for my x, y, and z axes. And here's the picture that I got. Looks a lot like, I hope, what we drew, right? There's that upside down parabola, the cylinder. The blue back here is x equals 0. That's the yz plane. And then this green plane here is y equals x. So you can see there's that curved surface and there's that flat surface. And if I rotate and look underneath, I can actually see this triangle here. That's that region R from our picture. So that's what it would look like in Maple. This last option is another free option that you can use. It's called Geogebra. You can see I've just gone to geogebra.org, and I just chose the classic option. And that also allows me to do 3D graphs. It's pretty simple. Start up, all you do is type them in. Here's my z equals 4 minus y squared, my y equals x, and my x equals 0. And here's the picture. I can once again do some rotating here. I can see from above there's that triangle, or I can see from below also that triangle in the xy plane. And I can see the three-dimensional chunk in here, whose volume I'm trying to find. So I encourage you to play with whichever of those tools you have at home in order to be able to see three-dimensional graphs. All right. So let's see, going back to our problem, my goal now is to find the volume of this wedge thing that we have now described, hopefully reasonably well, to ourselves. And to do a volume, again, I always integrate a height function. In this case, the height function, the z value, is this surface right here, right? Here's my height. So I'm going to integrate the function 4 minus y squared. Now to determine my limits of integration, I'm going to look at R. I'm going to choose, actually, you know what? I think I'm going to choose a horizontal rectangle this time. They both work reasonably well, but I'm going to go horizontal. If I go horizontal, that means I'm choosing to do dx first, and then dy. And I'm going to notice that the x values from left to right go from x equals 0 over to this line where x equals y. And then for my y limits, 0 to 2. Okay. So always using r to determine your limits of integration. All right, evaluating our integral now. This is actually why I chose to do the horizontal rectangle. This whole function is constant with respect to x. So at integrated, all I have to do is take the 4 minus y squared, the constant, and multiply by x. It's that simple. That goes from x equals 0 to x equals y. Plugging in the top limit, I'd have 4 minus y squared times x is now y. And minus, when I plug the x equals 0 in, the whole thing's going to go to 0. So I won't bother writing that term. And then I can just finish this up as a calculator problem. When I plugged it into my calculator, that integral gave me 4. All right, we will stop there for this video and pick it up in the next one.